Hello everyone. In this video, I will demonstrate how to perform exploratory factor analysis using SPSS. So as you may know that factor analysis is used as a most common method for the data reduction or as a data reduction technique. So if you have, let's say, 10 or 15 variables and you want to represent these variables using few components, so you use factor, or you could use factor analysis for that. So we want to use few components to represent as many as much variation in those 15-20 variables as possible. So this could also be used to find out if there is some underlying structure to the number of variables you have, or you can use those component scores in your further statistical analysis like regression or MANOVA. So without getting into much theoretical detail, I will show you here how to perform the factor analysis using SPSS, and what are the assumptions involved, how to deal with outliers, missing values, and briefly about the sample size. So this is the data set we're going to use for this one. So I want to perform the factor analysis to determine if any underlying structure exists for measures on the following 12 variables. So this is some sort of school data we have here. So we have the variables like person graduating in 93, 94, average ACT scores in 93, 94, 10 grade average score in 1993 for math, for reading, and for science, person meeting or exceeding state standards in 1994 for math, reading, and science, and then person limited English proficiency in 1993 and 1994. So we have 12 variables, and we want to see if there are any underlying structure exists among these 12 variables. So we want to use it as a data reduction technique, more kind of exploratory factor analysis, and we're going to store the scores as well for those factors so that we can use that in our future statistical analysis. So I'm using this book material here. This is a very good book on multivariate data analysis. So I insist you guys to go and read this book if possible. So without getting into any further detail, I would show you how to do the factor analysis using SPSS here. So I have this data here. That's the data we have here on those 12 variables. First of all, let me talk about the sample size. So to perform any kind of factor analysis, we usually need a big data set. How big? There is no such common standard, but a more acceptable guidelines are like, if you have one variable, for every variable you have, you should have around 10 observations. 20 will be the best. So if you have 10 variables, you should have around 100 cases or observations, and that's going to be good. But if you have 200 for 10 variables, that's going to be even better. So that's kind of common, understandable guideline there. But bare minimum, you need for every variable 5 cases. So if you have 10 variables, bare minimum you should have around 50 cases. And I'm talking about complete cases, not with the missing values. So that's something you have to keep in mind. So around, for every variable, I would target 15 to 20 cases to be comfortable performing the factor analysis. So first of all, we're going to see how many cases we have here. Obviously, we can just scroll it down and see we have around 64 cases among 12. So we have around 5 cases for each variable. That's bare minimum, but the focus here is to show you how to use the factor analysis rather than focusing on the sample size too much. So we're not going to go there. But first thing first, always keep in mind, bigger the sample, the better. The more sample data you have, the better will be your statistical analysis, because everything is sensitive, very sensitive to sample sizes. So keep that in mind. Secondly, let's go ahead and let's see how much missing values we have. So missing value have a dramatic impact on the statistical analysis. I'm not going to go into much detail about the consequences of missing values. We want to make sure that values are missing at random, completely at random throughout the data set. And there are a lot of statistical tests you can perform, but I would rather just scan through the data and see how much you see them. Are they concentrated on particular variable or particular cases? And here it doesn't look like that. We do have some missing values here. So I want to know the summary of missing cases. So the best way to do that is I'm going to go to analyze your descriptive statistics, explore. I'm going to use all my variable, the dependent list here. I'll go to the statistics here. I just want the descriptives. I don't want to do anything else here. Plot, I guess you have to bare minimum choose one plot. And I usually prefer the box plots as well. So I'm just going to show you that. But right now we are not doing univariate data analysis. So I'm just going to do none here. I have to select one, otherwise it won't let me do it. So I will just select the histogram here. But right now I'm more interested in looking at the missing values. Okay, so I'm going to say continue here. Option here, even explore, exclude all the cases listwise. Listwise means any case you take, if there are missing values for any of the variables, that case will be excluded from the explore. So we're gonna select that one and continue here. So as I said, my focus is just on case processing summary here. So it tells me, how many cases have missing values in all. So out of 64 cases here, we see that there are 3 cases where we have some sort of missing values. So we have 61 cases with complete data. So the missing values are only 5%, around 4.7%, so around 5%. So the deal here is, if anything less than 5% data missing, it's worth to just delete those cases. So in this case, we're just going to delete those cases, or in other words, we will not consider them in our analysis. So, but if you have missing values ranging from 5% to 15% or up to 20%, you cannot just get rid of the data, because it might bring down your sample size way too much. In that case, you usually go for some type of imputation, and the most common method of imputing the data when it is a ratio scale or interval scale is the average or the mean, or median, depending on which one is more suitable, mean or median. So these are the 2 most applicable methods. If you have a categorical data, then the most preferred method usually is the mode. So you replace the missing categories with the category that is most frequently occurring for that particular variable. So those are the most used methods, but there are more sophisticated ones that should be, you should always be using your domain expertise or some sort of expert knowledge to judge which method is the best. So we're not going to go there, we're just going to delete those missing values cases, or ignore those cases where we have missing values. Okay, another way to explore the missing value, which I really like, is if you go to analyze report case summaries here. Let's say select all our dependent variables here. I don't want to display the cases per se. I just want to know the number of cases that has missing values. So I will say okay here. So this basically tells you, for every variable, how many complete cases are there and how many are missing. So for LEP 93, you have full data here. For grad 93, you have 3 cases where the values are missing. So you have 61 complete cases. So this gives you variable wise descriptive statistics, how many cases are there for each variable. So here you can see the case summaries for every variable, how many complete cases are there. But it doesn't tell me, like, you know, the explore one, like in all, how many cases are missing values. That's the reason. But this is a good snapshot as well. But here, if you go up here, this, the first one we did, it tells me straight away like how many cases are there which have missing values. So keep that in mind. So once you take care of the missing values, the next step is finding out the outliers, because outliers have drastic impact on the analysis. And why is that so? Because, you know, even in the factor analysis, you find the linear combination or weighted linear combination of all the variables that forms a factor, and it's sort of a linear equation. And if there are outliers, you might not get the perfect you know, line that represents the weighted combination of those variables. So you need to take care of outliers. Now when you're dealing with the outliers, you can deal with univariate outliers. Like for every variable you can do the box plot and find out the missing values. But this is more kind of multivariate data analysis, factor analysis. So here we want to kind of deal with multivariate outlier. That's the priority. That's the priority, and much more kind of you know, better way to deal with the outliers instead of doing the univariate outlier. So we're just going to focus here on the multivariate outlier. Now what do you mean by multivariate outlier? What we do here is, instead of focusing on one variable at a time, we just gonna focus the combination of all 12 variables. And kind of, you know, so you have 12 variables and around 61 records. So for all this data set, multivariate data analysis, what we're going to do is we're going to perform what we call Mahalanobis distance. So what it does is basically it forms a global centroid for all the complete data set, and then from there it measures the center for every case, how far that case is from that global centroid. And if it is within the range, then it's okay, but otherwise it is considered outlier. So let's go ahead and do it, you know, in SPSS. Let's see how we can do that here. So to calculate the Mahalanobis distance, we go to analyze here, regression, linear, so to perform this Mahalanobis distance, we don't need any dependent variable as such. So we're just gonna put in ID there, and all our dependent variables in all our variables, like the interval scale variable, into independence here. Then we go to statistics here. We're not worried about the statistics here. Plots, we're not worried about the plots either. We want to save this Mahalanobis distance here. So we're gonna check that one here. Say continue here. Option, if you see here again, it exclude cases list-wise. So basically it only consider the cases that have complete information. So in our case, we have 61 cases where we have complete information. So rest of the 3 will be ignored anyway here. So we're gonna leave it like that here and say okay here. So since we saved Mahalanobis distance here, it will form additional column in our data set and save all these values, which I'm going to show you here. So once you say okay here, it's going to perform the analysis. And so if you close this one here, go to the right of your data set, it created a variable called NAH_2. So this is the Mahalanobis distance here. Now, you know, so let's see, I'm going to sort this, let's say, descending, so that the biggest distance appears on the top. So you see some of the distances from the global centroid are way too much, specifically, these two, 40 and 38. But we don't know whether they are statistically significant. So what we had to do here is we had to calculate the p-value using chi-square distribution. And the easiest way to do that is create another column here using compute variable. So we're going to go to the transform compute variable here. We're going to say this is the probability underscore MD for Mahalanobis distance here. And this is the way you calculate the probability. So 1 minus, we have CDF function here for the chi-square. And here, what we're going to do here is this is the Mahalanobis distance we just calculated here. So we're just going to drag this one here. Make sure you get rid of that question mark, okay? And here is degree of freedom, which equals to the number of variables we have in the analysis, which is 12. So I'm going to put it 12 and say okay here. Close this one, and it gives in the probability here, okay? So obviously, we want to another thing I want to point out here is the critical value here. The critical value is if the probability is less than 0.001, then it is term significant. So these two are less than 0.001. These two are considered outlier than straight, and rest of them are not. So we're gonna what we're gonna do is we're gonna filter our data set and exclude these two outliers here. And obviously the last three will be excluded because it has missing values, okay? So those will be excluded as well. So if I sort it again and say sort ascending, you'll see all of them coming on the top. So when we're gonna filter out our data, you're gonna see all these 5 rows will be crossed out here. So what we're gonna do is we'll go to the data, select cases, go to if here, if this probability here is greater than 0.001, so select all the cases where you have this probability is greater than 0.001, and that should be it here. So you say continue here, say okay. So you see it crossed out all those 5, 3 for the missing values and 2 where the p-value was smaller than 0.001. So so this is how you take care of the outliers. So once you're done with the outliers, then we have to check for the assumptions. So when you check for the assumptions, you have to check every variable for normal distribution, like every variable should be normally distributed. And also all the linear combination of all the variables must also be normally distributed, and the relationships among all pairs of variable must be linear. So these are the 3 assumptions you have to check. So when it comes to checking the normal distribution of every variable, we can again go to the analyze descriptive statistics and explore here. We already have those selected variables here. So this time statistics, we want descriptive statistics here. Plots, this time I want to go with the factor labels together. This is going to just produce the box plots for every variable. Stem and leaf chart, histogram here. I want the normality plots with tests as well. So let's check that one as well. Option is going to exclude the cases list-wise. Anyway, we have already filtered out the data, so it's not going to consider anyway. But again, just keep in mind that it's going to just consider the cases with the complete values. Okay, so continue here. Say okay here. Okay. So I like the browsing the data using this labels here. It's much faster. So this is the case summary here. So it gives you the case summary here, and it gives you the descriptives here. Okay, we're not worried about that, but I'm just going to jump on to LEP93. So you can see this histogram, it's clearly not normal here, right? And that will be reflected in the test of normality here. Test of normality, if you see here, it tells you that this LEP93 has significant KS statistics and SW statistics as well. Significant means this variable is not normally distributed. That's an alternate hypothesis. Um, uh, so the null hypothesis is these variables are normally distributed. So only you see that here, grad 93 and read 93, they looks like normal, and we can see that here. So if you go to the grad 93 here, grade 93 is very much look normal. You can see the histogram, you can see the stem and leaf chart also look kind of normal here. QQ plot is also looks like very normal here. And the statistical test, as we saw using KS test, was significant as well. And then the box plot is also very symmetric, which kind of tells you the distribution here is pretty much normal. But that's not the case with others like this ACT94. It's like skewed to the right, and so is the stem plot. It's very similar to your histogram here. So even the QQ plot, you can see that it's not normal, it's not matching. The all this dot needs to be as close to the straight line as possible for the data to be normally distributed. And this could be reflected by the box plot as well. You see that it's not perfectly symmetric. And you do have some univariate outlier, but we're not worried about the univariate outlier because we are doing the multivariate analysis. Our focus was more on multivariate uh, outliers, which we have already taken care of. But this is how you see the univariate assumptions of normality. Now we need to get into the multivariate assumptions of normality as well. So for example, any linear combination of all the variables must also be normally distributed. And this is one of the toughest tests to, it's not that easy to perform multivariate normality test, but we can always do bivariate normality test using scatter plot. And scatter plot can also be used to judge the linearity among all pairs of the variables that we have in the data set. So let's go ahead and do that one here. Just you can again browse through all the data and see. You must do that because it gives you more information about the data. You understand your data well, and if there are anything to be concerned about, you can take care of it right now here before you go to advance into analysis. So with this univariate assumptions taken care of, let's move to multivariate assumption, at least bivariate normality and linearity here. I'm going to close this one here. Okay, and I'm going to do the scatter plot. Now to do the scatter plot, chart builder, you can do that. If you go to chart builder, say okay here, you can just select the scatter dot matrix here and select all your variables here. Put it here and say okay, but this is not working for me for some reason. I don't know, it's just throwing the error. I don't know what this error is, but what I can do is if I go to the graph and legacy dialog, it works for me. So I'm just going to show you that one as well. So if you go to the, let's say, scatter or scatter plot here, say you want to do the matrix scatter chart, and then there you put in all your variable here. Say okay here. Now it produced the scatter plot. Now this is very small here, but this is the same thing as you have gotten using the chart builder. So same thing, we're gonna make this chart a little bigger so that it's more easy to see. We're gonna populate the diagonal with the histogram so that we can see the univariate normality right then and there, even though we have already gone through it. And we can draw the line here, the regression, the best fit line as well. So let's do that. Double click on that chart here. So it's going to open up chart editor. Double click here again. It's going to open up the properties. I'll go to the chart here. Let's say I want to say this is like 700 width. Okay. I'm going to apply this one. So it's going to make it bigger. Let's draw the regression line. So this is the icon here. Add fit line at total. So I'm going to click on that one. So it's going to add the regression line to the data. And we go to the options here. And I want to show the chart in the diagonal. Okay. So we are done with this one. So I'm going to close this one. I'm going to close this one. So this is our kind of chart here, right? So here you can see that, you know, on the diagonal you see all the histogram for every variable, and then you also see the regression line. Like most of these bivariate relationships are pretty cool, pretty good here. Some of them are a cause of concern. You can always always transform these variables here, but I'm going to leave it like that. One thing you need to understand here is, you know, we are performing exploratory factor analysis, and it's been mentioned in many literature that when you're doing exploratory factor analysis, all these assumptions are not strictly accountable as such. So keep that in mind. We are checking for this assumption because if we satisfy these assumptions, we get more reliable results, no doubt about that. But we can still go ahead, even if we are not meeting these assumptions to a certain extent, we can still go ahead and perform factor analysis, and that's what we're gonna do here. Okay. So, but at least we know how to do the scatter matrix, scatter plot here. See the linearity here. Most of them are pretty good, but some of them here and all this here are not that good with the LEP93 and LEP94. So clearly that's not normally distributed or not even linear, but we're gonna leave it like that and we will move on with our analysis. So once we have taken care of the sample size, the missing values, the outliers, and the assumptions, the next step is to go ahead and perform the factor analysis. So we're gonna close here. And I will go to analyze dimension reduction factor. I'm going to choose all my factors there. I will go to the descriptives. I want, let's say, coefficients here. It's going to populate the correlation matrix here. Reproduce correlation, KMO and Bartlett's test of sphericity here, so we can check that one as well. We're gonna get the initial solution here. Extraction method we want to use based on eigenvalue. So anything that is more than one eigenvalue, we want to retain those component here. We want unrotated factor solution. We want Scrib Plot here. Continue this one. Rotation, we want to do the Variance rotation, which is sort of orthogonal rotation, which means that factors or components will not be correlated to each other. So they will be orthogonal to each other. So that's what we're gonna do. But if you feel that there could be some correlation between the factors, you can do the oblique, the direct oblique method as well, but we're just gonna pursue Variance rotation here, and we are interested in rotate solution, so that's gonna be there here. Scores, I want to save the scores using the regression method because I can be using this component in the future statistical analysis, for example, multiple regression or MANOVA or ANOVA. So I'm going to save that as using the regression method here. And options, again, if you see factor analysis is always performed using complete cases. So it excludes cases listwise. So that will be there as well. Continue this one, say okay here. So here it gives you the correlation matrix here that shows you the correlation between the variables. Now understand one thing, that factor analysis thrive on high correlation between the variables. So we are, if you do not have if these variables are not correlated to each other, then you cannot do the factor analysis. So in other words, let's say there are zero correlations among all these variables. So maybe, so if you perform the factor analysis, then since these variables are not correlated to each other, you'll get 12 factors. Okay, but if they are highly correlated to each other, then we can explain the variations in all those related variables using few components, and that's the focus here. So you can always browse through this matrix here. You see that there are some high correlations here. Math 93 is highly correlated to grad 94, ACT 94, ACT 93. All these are high correlation here, so maybe they're gonna hang out together in the analysis. So this is just for browsing through the correlation matrix. It doesn't give you a lot of information here as such. But then we perform the KMO and Bartlett test. KMO measure of sampling adequacy should be greater than 0.5. It's 0.896 here, which is good. What it does, it measures how much common variances are there among the variables, or how much shared variances are there among the variables. Its value ranges from 0 to 1. So if we are closer to KMO, measure of sampling adequacy is closer to 1, that means you have more shared variances are among these variables. So it's always good. So here it's the minimum should be again around 0.5, and it ranges from 0 to 1. So here we are getting almost 0.9, which is very good number here. So, and the Bartlett test of sphericity kind of test among all these correlations you see there. It tests that at least there are some variables where the correlation is significant. Again, that might not give you a lot of information, but it's a test. It's making sure that there are at least some variables where the correlations are significant. So if it is 0.0 here, that means this is statistically significant, and we do have some variables where the correlations are significant, and as a result we can go ahead and do the factor analysis in nutshell. Although keep in mind that all these tests are very sensitive to the sample sizes. Okay, and also that's something you have to keep in mind. Now the next table here is, okay, so I'm going to close this one. Okay, so next table is communalities. Now, what is communalities? It tells you how much variation from that variable is being extracted by this component solution. So, for example, LEP93, out of 100%, you're extracting almost 99.3% variations in that variable. And since we are using eigenvalue approach to find out the number of components, like we are seeing that if the eigenvalue is more than 1, then we want to retain that component, and that criteria only works if most of the time your communities are greater than 0.7. So here we see that all these variables have communalities more than 0.7. Again, it tells me, for example, let's do science 94 ME. It tells me that out of 100%, I'm extracting 94.5% of the variation from that variable. You want to extract as high variation from that variable as possible using the fewest number of components. So that's the communalities here. And then the next one is total variance explained. So it tells me that how many components are being extracted. Since we are using rotation, varimax rotation, so we're gonna focus on rotation sums of square loadings. So basically it tells me that there are 2 components that must be retained and these two components together are extracting 91.74% of the variations among all those 12 variables, which is excellent. So the first component is extracting 74%, 74.73% of the variation, and the next component is extracting 70.01% of the variations in the data sets. Together, they're extracting 91.74%, which is again very good. That's what that was based on eigenvalue. The second approach is to find the number of components you want to retain. You know, also see the Scrib plot here. Now the Scrib plot tells me that you must be retaining 3 components, because after the third one it kind of levels off, but our eigenvalue is saying the 2 components. So again, you know, there is no hard and fast rule. These are all very generic criteria. I have given the rules here. If you're using Scrib plot, retain all components within the sharp distance before eigenvalues level off. This criterion is fairly reliable when the number of individuals is greater than 250 and communities are greater than 0.3. So in our case, we have a very small data set, so Scrib plot may not be as reliable. You can also use variance approach, like retain all the components, extracting at least 70% of the total variability. So if you go with this one, you see that the first component is just gonna give you 1 component, because our first component itself is extracting 74%, which is more than 70%. But eigenvalue looks more reliable here, because second component is, when you add the second component, we are extracting a lot more. And the final criteria is the residual matrix. So retain the components generated by the model if only few residuals exceed 0.05 value. So I'm going to go and do that. The residual here, residual correlation. Now, briefly, what is residual correlation? We have original correlation metrics here. Okay, these are the original based on raw data, and reproduced one is based on the factor solution we just created. So it kind of does the reverse engineering. It takes the factor solution, and from that solution, it try to come up with the correlation between the variable. And if the factor analysis has done a good job, then the reproduced correlation should match with the original correlation. And that's what this residual tells you here. The residual is basically the difference between the original correlation and the reproduced correlation here, and the difference are given here. Now it tells you that here that residuals are computed between observed and reproduced correlation, and there are 5. That is 7% of the non-redundant residuals with absolute value greater than 0.05. 7% of the correlations, total correlations, is very small number, so we can just see that our factors are doing pretty good. We want this number to be as low as possible. So only 5 out of so many are like good thing. So we this is further buttress our solution of 2 components. So we're gonna go ahead and retain 2 components here. So that's how you figure it out, how many components you want to retain. Again, it's very subjective. It all depends on a lot of other factors as well. I would say that you have to trust more on your judgment, intuition, and your experience and domain expertise when deciding on retaining the number of components. Okay, so once you decide on how many components you want to retain, the next thing is go ahead and interpret the components here. So I'm going to go ahead and see the rotated component matrix, because we are using Varimax rotation here. And one thing I should have done, which I haven't done, is sort this loadings here. So I'm just going to go ahead and perform the analysis again, because I wanted to see the sorting here. So I'm going to close this one here. I will go to analyze dimension reduction factors, go to options here. I should have checked this box here, sorted by size. Okay, and so okay, here we already gone through all of these things. I'm going to go to the rotated component matrix here. Okay, and this tells you the factor loadings. Okay, these are all called loadings. Now, what is the factor loading? Factor loading is kind of a correlation between the variable and the factor. Higher the better. So all the highly correlated factor loadings will come together and form one factor. So if you see that all these one are pretty high, they are supposed to be, the normal rule is if if you have a fairly big sample, so this component loading should be greater than 0.3. That's a suitable general guideline. So here we have much higher than that. So I can see that all these positive loadings are going to come together and form one factor. Again, this is very much like a correlation between the factor and the variable. Okay, so all these thing up to grad 93 is going to form one factor here, and last two one LEP 93 and 94, they tend to go with the second factor better. So second factor will have, or second component will have these two variables, and first component will have these 10 variables. Now, if you see that most of them are math, read, science, kind of related variable, ACT variable. So how would you name this factor? Probably I'll go ahead and name this one as academic achievement, because they're all related to academic achievement here. And these are two specifically related to English proficiency. So I'm gonna just name them English proficiency as a factor. So this is how you interpret the factor, you name them, and we already saved the score. So I'm gonna show you the score. But before that, this tells you component transformation matrix. This basically tells you the correlation between the factors we just created. So we have two factors, and we went for varimax rotation or orthogonal rotation. So that's why you see that they are not correlated at all. So 0.01 is nothing. So they are not that correlated, and that was expected. So this is how you perform the factor analysis here. I'm going to quickly show you the score here. So it added, we did it multiple times, so it added, again and again, but these are the last two you consider. These are the two factors you added. First factor, I'm just gonna go here, I'm gonna rename them. Let's say I'm gonna call this one as achievement. Okay. Achievement, and here I'm going to say English proficiency. Okay, so we name this one so that we can, instead of now using those 12 variables in our analysis going forward, like if you're doing regression or MANOVA or ANOVA, we can simply use these two as a representative component, because using these two components, we are extracting almost 90% of the variations. So this is how you perform factor analysis. Thank you very much for listening.